Okay, so first law of thermodynamics. Okay, so the first law of thermodynamics is, I like how this joke says, you can't win. So literally, I was prepping for this video and my husband saw, and he comes over here and he goes, "Hey, remember that equation? Remember I told you how in thermo, it's like the simplest equations and it's like the most awful thing in the universe?" And I was like, "Yeah, I literally just said that in the previous video." So I'm letting you know that 25 years later, this poor man is still like completely triggered by internal energy equaling Q minus W. So it's okay if you're just completely done. And it's the end of physics one and it's okay. Okay, so basically, okay, here's what we have. I'm going to try not to scare you off of the rest of your science profession now. Okay, we have Q represents the heat exchange between a system and the environment. So Q is heat. Q is heat and W is work. So what we're going to call internal energy, energy, internal is going to be heat minus work. Okay, so in theory, when heat is added to the system, we can have added to the system, in which case it's positive, or taken out, in which case it's negative. Work can be done, let's see, when work is done by the system, work is done by the system, work done by the system, by system, it's subtracted out, which is weird because it's positive, but it's subtracted out. So I'm going to say if it's work done by system, it's subtracted out. I can't spell. Subtracted out. And if the work is done on the system, it's added in. So maybe I kind of like want to rewrite this equation. Hi, I am a person who is not a thermo expert. I'm going to rewrite this equation just for a second. Internal energy, internal energy equals added heat plus work done on system minus heat taken out minus work done by system. Okay, those are all words that make sense to me. Okay, I'm going to keep coming back to that because the words make more sense to me than the letters right now. So the total internal energy is going to be any of the heat we've added to the system, any work we've done on the system. Well, that makes sense because work we've done on the system adds energy. Heat we put adds energy. Any heat we've taken out of the system takes away energy. And any work we've done, any work the system has had to do makes it tired, so it has less energy. Okay, I like that. So that's how internal energy is defined. Okay, I'm going to come back to that later. Okay, but it's called heat exchange. So that makes sense. But here's all these conventions. Okay, so the first law is a statement of energy conservation. Now, here's the thing that it's going to say, and you're going to skip it if you're just reading it, but it's really, really, really important. Okay, hold on. It says here that the change in the internal energy of the system between A and B is path independent. So you remember how in potential energy, like we said, if I'm here and then I go and I fall here, it's just MGH, right? It doesn't matter which path I do to get to MGH, it's just MGH, right? Um, but there were certain things that were path dependent, like friction was path dependent, but like There were a lot of forces that did work that was path independent. Well, this is the same thing. So internal energy that happens like from A to B is path independent. So once I figure out whatever the internal energy to get from A to B is, it doesn't matter how I get there. That's just the energy to get from A to B. So if I can find it for one path, that works for all the paths. So that's really, really important. Okay. Um, so yeah, we're going to go with that for a minute. They're called state functions, and that just sounds fancy, like you have to wear a bow tie. Um, okay, and then look, let's write it in terms of differential equations. That won't look scary. Okay, let's just try and do a problem and see if that can happen. Okay, during a thermodynamic process, a system moves from state A to state B. It is supplied with 400 joules of heat and does 100 joules of work. For this transition, what is its change in internal energy? Okay, so really, it's not even its internal energy. What I should have written over here is change in internal energy. Okay, okay. So come back here again. Whee! Okay, so this dude has a. I'm going to try not to look at the answer. Oh well. All right, so I have a change, but this is part A. So the change in energy to go from A to B, I have 400 going in and 100 going out. So its change in energy is 300 joules. Yay. Okay. Now, if the system moves back from B to A, what's its change in energy? Well, if it's closed path, it needs to be 0. Did I say that? Well, that's the same thing with potential energy, right? If I go and I ended back where I started, potential energy is 0 because no work has been done, right? We end up where I started. So the change from A to B plus change B to A would have to be 0. And since this one is 300, that means that change B to A would have to be negative 300. Did I get that one right? Yay. Okay. And then the last question says, if in moving from A to B along a different path, 400 joules of work is done on the system, so how much heat does it absorb? I don't know. Okay, so let's look at part C. Okay, well, it's moving from a different path from A to B. It has to be 300 joules because here, so it has been declared. Because it's path independent, so it doesn't matter what path I take, that has to be the answer. Okay. 400 joules of work is done on the system, so I've put in 400 calories or joules. So how much heat does it absorb? So plus, what was heat? Heat was Q, because W was work. That has to equal 300. So Q must be minus 100. So I guess that's the absorbing part. So it must have absorbed 100. There you go. Okay, look. See, this is what I'm saying. Is I don't know, maybe I'm just tired because, it's end of semestery stuff. I'm literally just doing 400 minus 100 is 300. 400 plus is 300. What's And what's negative 300? Like this should not be hard, but I'm here questioning like do birds really exist kind of a thing. Okay, so this is basically what we're going to be doing with thermo is very, very, very basic math and questioning, fundamentals of addition and arithmetic.